Okay, so now I'm going to tell you about another technique which is a bit closer to research. It's not going to be so standard, so it's something which we've been using recently to look at Majorana states. So, you're not going to find it in courses, but I'm going to tell you about it, and also it gives you the opportunity to tell you about a classical technique which is used in condensed matter, which is T-matrix, so analyzing the impurity states associated with a given impurity. So then I thought it was a good opportunity because first I'm telling you also about the way we obtain Majorana with this technique, and second you find out more about this T-matrix technique, which is very standard and I think very useful to know for the students. Okay, so I told you that about tight binding, and I told you about this type of matching, solving the Schrödinger equation, methods to get Majoranas. So now I'm going to tell you about obtaining Majorana states via different techniques, and what do we do? I told you if I have an infinite system and I cut it in the middle, if my system is topological, I'm going to have two bound states, two Majorana states, which are going to form on the right and on the left of the cut. Most of the time we don't think about it like that. We just say, oh, well, I have a finite system, at the end I'm going to have Majoranas. But I'm thinking about it in a different way. I'm saying I have an infinite system and add a cut in the middle, and then I have to get two Majoranas. But what we thought was that can we get Majoranas by adding first a small impurity inside one of these topological systems and letting this impurity going slowly to infinity, and then when this impurity potential went to infinity, I'm going to form two Majorana states on the right and on the left of the impurity. We asked the question, and it turns out that the answer is yes. When I'm solving the problem of the impurity, when the impurity potential is infinite, then I'm actually getting the Majorana state. And the advantage of this is when I have a localized impurity, I have exact solution in quantum field theory to solve the problem. Because I know that I have a localized impurity, the problem of a localized impurity can be solved exactly in quantum field theory, but we call the T-matrix. So then, no matter the bulk, so no matter how complicated the bulk is, when I add one of these localized impurities, I can get the boundaries. So this is very nice because I can get exactly the solutions of the Majorana without going through either numerics nor approximations. I don't have to do any low energy approximation. I don't have to do this type of solving the Schrödinger equation problem, which is, as I told you, complicated, not very general. But I can get the solutions for any bulk topological systems without any problems. And it also works in 2D. So it works in 1D, but it also works in 2D. If I have an infinite system, I add a line impurity this time. Not a point impurity, but I add a line impurity. When the potential of my line impurity goes to infinity, I form two states on the right and on the end of, on the right and the left of the impurity, and these are the Majorana states which are propagating, which I showed you before. So these techniques allows me to solve for Majorana 1D states and 2D states without any problem. So I'm going to show you the T-matrix technique first, and I'm going to give you some example of how this technique works for 1D and 2D systems. So the algorithm, the general algorithm is to take a system, infinite 1D, or that can be 2D or 3D, then introduce the point-like. For the 2D it has to be a line-like. For the 3D it can be a plane-like, so it works also in 3D. So I can get surface states, not only edge states, but I can get surface states in 3D. And this impurity is described by a delta function potential. Then I use the T-matrix formula to find the energy and the eigenfunctions. And then I set the impurity potential to infinity to recover the formation of the boundary mode. Okay. So this is the algorithm. But before I give you some results and some applications to Majoranas, I'm going to tell you about the T-matrix formula, which is, again, I think quite important to have some idea about. Okay, these are the results. So I'm going to just go back to the board, and I'm going to tell you about the T-matrix. Oh, it doesn't matter. It can be any Hamiltonian you like.
But if the system is continuous, then the delta function cannot divide the system into two.
Yeah, well, we usually apply it on the lattice because it's much simpler, because I can have impurity sites which are on the. But then when I go to low energy, it's the same physics as the physics of the continuum. When I go low energy, then the discrete system is basically the same physics as the continuum system. it's just a grid. I mean, you know, I'm using a grid to start with, but at the end, I mean, when I'm low energy, it's the same as the physics is the same. It's only that the grid is very small. So, okay. Okay, so T-matrix approximation is the solution. Is what some people call it differently, because some people talk about T. When they talk about T and the T-matrix, they think about transmission and reflection and scattering, but this is not that. So this name maybe is not universal. We call it T-matrix, but some people call it T-matrix also something about scattering. It's not about you know, reflection and transmission for a conductor. This is just solving the problem for a system with localized impurity. So I have an infinite system. I'm adding a localized impurity. Okay. Okay. So I have an unperturbed H0. This is the bulk Hamiltonian. The system is infinite, the bulk system. And then the impurity, so I have H0. And I add the impurity potential. I'm going to focus on 2 dimensions, but it works in 1, it works in 3D. So that's the form of my impurity potential. It's a density potential, so I'm adding like a local chemical potential, which is very large. And this V of R, in order for this problem to be exactly solvable, is a delta function potential. So I have an impurity which is localized at the origin. Okay. Now, if you look at the form of the Hamiltonian momentum in real space and you go back to momentum space, so you now Fourier transform C of R and C dagger of R, then you're going to get K2. And then you have a delta of R here. So you said when you do the integral over R, with the delta of R, this gives you a constant, and the potential in momentum space is independent of K. So what happens is that you have scattering which is independent of momentum. So I assume I have my impurity. I have a particle with K1 which comes in. It can scatter with equal probability in any momenta, in any other momentum. So any incoming particles, it can scatter with the same probability in all the other momenta. So this is called momentum independent scattering. So this comes from the form of the potential which is localized, which is delta function. And this is very important because this is what allows us to solve this matrix. Okay. So how do we treat an impurity? What we're going to do, I'm going to use perturbation theory and write down all the orders of the perturbation theory in the impurity, and we see that we can sum up actually the sum of all orders in perturbation theory. And that's what they call the T-matrix expansion. So, but in order to write the perturbation theory, I'm just going to give you the definitions, which you probably know, of the Green's function, because we are going to work the perturbation theory in the Green's function. So we're going to work also in imaginary time, actually imaginary energy. So we're going to use Matsubara frequencies. So we know that in imaginary time, we can define this type of Green's function. So the omega n are the Matsubara energies. I'm not going to get into Green's function theory. Probably took some field theory classes, but I'm just going to remind you the definitions. You can think about this type of Green's function as correlators between two so this is like a 2-point function between the fermion with momentum K2 and the fermion momentum K1, and they're evaluated at energy omega n. And in imaginary time is very simple. They are like they're just correlators, side correlators. When I have to go back to real time, then it's more complicated. But in imaginary time, it's very simple. And that's what allows us to do a lot of calculation, because we work in imaginary time, and then things are very simple. But these Matsubara also have the advantage that when we go back to real space, we can go back to real space very easily by doing this transformation. Let's call it M. When I'm changing the energy, I'm doing this analytical continuation, I'm going from I omega n to omega plus I delta. This Matsubara Green's function becomes a retarded Green's function, which is a real-time propagator, whose definition I'm going to write down because it's complicated. But what's important is this is what captures all the physics of my system. The retarded Green's function is telling me everything about the elusive state, about the spectral function. The definition is quite messy, but its physical properties are very nice, because from this thing I'm going to get everything I want. So in particular, I can get the spectral function. And all the physics is in this quite insignificantly looking plus I delta. If I put a minus I delta, there's the advanced Green's function. It's not so interesting. But all the physics come from this plus I delta. So this is what we put by hand, and this is what all the physics is coming from. We can set delta to 0 at the end, or we can keep it very small. And this delta is actually, again, the inverse quasi-particle lifetime, what I was telling you before, for the width of a level. This is the same quantity, more or less. And the retarded Green's function is giving me the spectral function, and the integral of the spectral function over k is the density of state. So this is giving me all the physics. So if I solve my problem in imaginary time, then I can very straightforwardly go to physical quantities, because this is what matters, this type of quantities. So I'm going to write the perturbation theory in imaginary time. And solve it for this type of quantity treating. I'm going to start with the simple Hamiltonian, just for. Actually, I'm not going to start with Hamiltonian, a precise Hamiltonian. I'm just going to remind you that if this is my Hamiltonian, then, for example, G0 is going to be just. Probably remember that if my Hamiltonian is very simple, then this is the retarded Green's function in k omega. It's just the inverse of this, because I have an action, I get the ddt. The ddt gives me an I omega in the action, and then when I take the inverse, then the inverse, when I do path integrals, is going to be just the coefficient of ck dagger term, and this is just I omega n minus epsilon k. Probably everybody knows that I'm not going to go into details all the field theory, so I'm not going to tell you how to derive the form of the Green's function. Okay, but okay, now I'm going to tell you about the perturbation theory. So if I want to calculate the perturbed Green's function, so now here, if you look at this type of form, you see that I only have one momentum. And why is that? Because I can have propagators like that. Okay? But if my system is spatially invariant, if my system is homogeneous, I have no impurities, then I have momentum conservation. So I cannot have this to be non-zero if my system is translationally invariant. If my system is uniform, this is going to be proportional to this. Okay? So the Green's function for an infinite system has only one k indices, k index. It doesn't have two indices, even if I could write something like that. I mean, nobody stops me. But in general, if my system is spatially invariant, I have no breaking of momentum conservation, so I have the same k on the right and on the left. However, when I have an impurity, this is no longer the case. My impurity breaks the spatial invariance, so I'm going to have, in general, A Green's function will look like that. It's going to be dependent on K1 and K2. It's not going to no longer look just as a psi k dagger. It's going to depend on two momenta. Okay? It's not going to depend only on one moment. It's going to depend on two momenta. And this we call the generalized Green's function because it corresponds to spatially non-spatially invariant system. Okay. And this function, which I'm going to represent it something like that, like a line, K1, K2, is going to be equal to the perturb with a non-perturbed Green's function. And this is going to be a line like that with K1 equal to K2. And then I'm going to add the corrections due to the scattering by the impurity. So the first one, let me draw it first. I have an incoming particle, gets scattered by the potential, and it goes out. Okay, this is G0, this is G0. Okay, so this is the first order perturbation theory. And the term, if I write it in is going to be V. If I wanted to keep very general, I'm going to keep K1 and K2 indices in the V, but at the end, V is independent of K1 and K2. But I'm going to write it like that so that you see why the assumption that I have a localized impurity makes me able to solve the T matrix. Okay, so, but I can, in general, I can have any type of potential. I can have potentials which are going to be dependent on K1 and K2 if my impurity has like some sort of strange shape. Okay, so this is like the first term. And then let me erase this part. And then the second term. This one. Okay, I have double scattering, so this is the second term. And the second term, if you look, I have a K prime free variable in the middle, so I have to integrate over it. So it's going to be an integral over K prime. Then I have G0 of K1. I'm neglecting the omega because it's going to take taking too long. K1 K prime, G0 of K prime, V K prime K2, G0 of K2. Okay. And then of course I write up all the orders, like that, taking into account all scattering processes by the impurity. And you see that this is a sum. And we are going to use a trick to be able to sum this expansion. What I'm going to do, I'm going to define what I call the T matrix. Okay, T of K1 of K2. I'm just cutting the legs of these diagrams, more or less. Okay. Oh, sorry. And I'm going to define the T matrix, just the part which is in the middle. I'm going to define the T as being V is going to be the sum of all these terms. Okay, and if you look here, you see that this T, which has this form, appears here. Actually, it's going to appear in this expansion as the multiplication of this part. Okay, when I look at all the terms, I can see that T is V plus K1V and then T. T appears here, you know. T is like, if I write, no, let's write the second term because it's K1, V, V. If I'm looking at the coefficient of this term, you see here I have a V, and here I have two V's, and then I have three V's. So basically my T, which is the sum of 1 V, 2 V, 3 V's, it can be written as V plus V1 multiplied by T. I mean, it's just graphically, if I look at it, I see that this is how it works. by definition. This is just the definition of the T matrix. So I can write that in like that. Sorry, 3, 2 is just K1, K2, V plus K1, V, T. Okay, so this is exact. No more expansion. This is an equation for T. And I'm going to write it in explicitly because this is graphical. So this means that K1, K2, omega n is V K1, K2 plus integral over K prime V K K prime G0 of K prime T K prime T2 0. But now, if you look at this equation, you see that if V is independent of K, then T is independent of K also, and you're going to get a T which only depends on energy. I mean, of course, if V is independent of K by construction, T is also going to be independent of K1 and K2. I mean, if V doesn't depend on K1 and K2, this sum is not going to depend on K1 and K2 either. So I can write it V plus integral of K prime V G0 of K prime okay, of I omega n. And this is just a linear equation in T, so it can be inverted immediately and be solved. I'm leaving it in this form because sometimes T's and B's are matrices. Here are numbers, but sometimes they are matrices if I have internal degrees of freedom in my Hamiltonian. But you see, it's very important that I have a localized potential. If delta V is not localized, then V K1, K2 depends on K1 and K2, and this sum cannot be performed. It cannot be, this integral equation cannot be solved. Imagine that V depends on K prime, T depends on K prime. There is no way to solve this equation exactly. I have to make some approximation, I have to do some expansion. The only way I can solve it exactly is when V doesn't depend on K and T doesn't depend on K. That's when I can solve it. But it's very nice because I can solve it. I mean, so if I can solve it, you know, even for a localized potential, already I'm in business because it's not a very straightforward problem, and I can solve it exactly, and I get 1 prime V 0 to V, so T. So that's the solution. If for a very small V, you see that T is just equal to V. This is the Born approximation. For V is very large, you see this is very different than the Born approximation. It's very, very different because this term is can be neglected, and it's something like the inverse of the Green's function. So it's very different for very large V's. So this is quite, interesting formula which gives you a lot of physics when V is large. When V is small, then again it's just the Born approximation, simple. But when V is large, things are much more complicated. And then going back to the definition of the T matrix, you remember the diagrams I drew. It was just the T is just cutting the legs of G back, more or less. The T was just G without the legs. So I'm putting back the legs and the non-perturbed thing. So it was the unperturbed thing, and then I'm adding the legs back on the T. I'm just adding the two Green's function on the sides. You remember that the T was just this. It was cutting the legs of the G. So it was the G0 and the G0, and then I just cut the legs to get T from the G. But so then if I want to recover the G back, I have to put back the legs, so I'm just multiplying T by 2 G0s on the right and on the left. Okay. So that's the full form for the generalized Green's function. One depends on K1 and K2 in the presence of a localized impurity. That's how this is calculated, with T being this thing. So that's very useful for us. I don't know if you've seen it before, but this is some very useful calculation that we do for the localized impurities. And it also goes back to real space. If I want to do real space calculations, this is easily Fourier transform in real space, even into a simpler form. I get that. Remember that this Green's function in real space depends only on the difference between R1 and R2 when the system is translation invariant. But here it's going to depend on the full thing. So the unperturbed thing depends only on the difference between R1 and R2 because of the spatial invariance. But now it's going to depend on R1 and R2 separately. Well, okay. Do it like that first. I'm writing the full thing first. So this is the full formula. I'm having a T which was not localized but had an arbitrary dependence on R. So now if my impurity is localized, so T is independent of momentum, this integral is very simple. It's just a delta, this T is just a delta function. So then this is just d0 of minus R1 T of I omega n of d0 R2 R2. So in real space, momentum, the generalized Green's functions look like that. It's a product of two Green's functions and T matrix that has exactly this form. And if in a given system I have the Green's function as a function of position, then I immediately get the generalized Green's function, and from there, the local density of states, or maybe I write it in a nice way. I can derive the local density of states. For example, you remember that's what I plotted before. The local density of states as a function of position and energy is just minus 1 over pi imaginary part of G of R. So it's evaluated at the same position, and instead of omega I omega n, I'm going to V plus I delta. So that's the local density of states if I have the Green's function in real space. I can get it immediately. Okay, good. So that's the formalism for the T matrix. So do you have any questions? I mean, this is like the theory of the basic thing for the localizing theory. If you have any questions, feel free. So now I'm going to tell you more about the results that we obtain when we use this technique. And now I'm going to go back to Majorana and the Kitaev model again and again for the 10th time. So the Kitaev model, chemical potential T and delta. Again, this is the Kitaev model. I'm adding a potential here, has some value u, a delta function of position, and then this is the diagonal term. One is C dagger C, and this minus 1 is C dagger. So like I told you before, this is the electron component and the Hall component. That's why they have opposite sign. And I'm solving the system using this technique, using the T matrix. And I'm plotting the energies. The energies are basically the poles of the T matrix. So my T matrix is going to have some poles, and these are giving me the energies of the bound states. So if I have the impurity, I'm going to get that this T matrix actually looks like. I'm going to have some sort of peaks. Okay. And these peaks are actually the energies of the bound state. You see that when it appears here, this T, then it's going to is going to, and it has peaks, then there are going to be peaks appearing in the local density state. So these peaks are exactly the peaks corresponding to the bound states associated with impurity. So here I'm plotting the energies of these peaks appearing in the T matrix as a function of u, and then I see that when I'm going to a very large u, like I said, when I'm going to an infinite potential, which cuts my system into two, then the energies are going to 0. So these states, which appear at very large potential, are going to be Majorana. Their energy is going to 0. And we have some analytic form obtained with this technique. When you go into infinity, the energies basically just go as 1 over u, and it goes to 0 and u goes to infinity. And we also have some analytic techniques based on this approach to calculate the wave function when u is going to infinity, and they look like that. And if you look here, it's exactly what I showed you when I calculated the wave function of the Majorana. For positive x is 1, 1, and for 1 minus 1 here, and for negative x was 1, 1. So it is Majorana because the electron and the whole components are the same. It has some decaying coefficient. See, this is not an approximation. It was not so simple. It was just not m over v, but it has a more complicated combination of t, mu, and delta. It has this 1 plus delta over t log what blah blah blah. So the decay of the exponentially localized Majorana state has it's some more complicated form combination of delta and t, and also has some oscillatory part. You are going to see in many Majorana problems there is always some sort of oscillatory component, which we didn't have in the previous thing because it was like a more cruder approximation. But in general, there is also some oscillation of these Majorana states with position. So there are like some decay. There is some oscillatory term, and there is this electron-hole combination, which is going to tell me that I have as many electrons as holes. So this is a Majorana state. So and this is obtained fully from this technique.
Pi over 2 is the fermion.
Yeah, yeah, because you are at. I think you are at. Yes, you are at. Exactly. You are at half filling. Yeah. I don't even know if you can write exactly this form for all chemical potentials. It may be more complicated. You have to do the integrals, and it's more complicated for the other values of the chemical potential. It's Vardan who calculated this exactly. Remember, Vardan, you sent me his CV like many years ago when he applied from Russia. So, sorry. No, I mean, it's just somebody, they got his application and they sent it to me because I was interested in students. Oh, but he's a nice guy. Okay, so now another example of case for which this method is working, and this is a 2D system. And you remember this is a slide from the previous lecture. This is not Majorana, but it's a topological. This is a topological insulator. It also exhibits edge states. It's not Majorana states, but they are conducting states, and they also are formed on the edges of a ribbon. Here the Hamiltonian is a bit more complicated because I have a hexagonal lattice. So I showed you before numerical results obtained by the tight binding model, or obtained using the tight binding model, what I showed in the previous lecture. So these results, this band structure is obtained using the tight binding. And you see that you have some low energy states, in-gap, sub-gap states, which are being formed in this topological space, and these states are localized on the edges, and they are conducting. So this is like the Kane-Mele model, topological insulator. So it's an insulator which is because it's gapped in the bulk, but it exhibits edge states which are conducting. So this is a topological insulator, and its physics is coming from the spin-orbit coupling, which is a next to nearest neighbor, in this case, spin-dependent hopping. So this I explained you in the previous lecture. I'm not going back to the details, but the idea is that you could obtain these edge states using tight binding. So this is what you have here, and again, this is a tight binding result. And when we do the T matrix, our T matrix calculation, we look at the spectral function, which, like I was showing you, it's coming from the product of the G0 T and G0. The G0 are the two one per third, and the T is the T matrix. And if I look at this spectral function, it's a bit more complicated in the spectral function because I'm averaging also along the along the direction perpendicular to the edge. So I have to integrate. I have to do an integral, so an average of the spectral function. But I'm not getting into those details. But if you look here at the equivalent of the spectrum, so the spectral function is giving you the states. You know, how many states do I have at each energy and at each momentum? You see that if my impurity potential is small, I have some subgap states, but they are not low energy. But when the impurity potential is going to infinity, you see that I recovered exactly the same state as by the tide-binding model, I guess. In my impurity is a line. It's not two lines, it's only one line. So I only have one line here, yes. So these two are matching exactly. So the tide-binding model and my technique, which is based on the T-matrix, are matching exactly. And I'm very happy because this you need to do a diagonalization of a lattice which is hexagonal. So this is ugly, and I would have never been able to do it without my students and postdocs. Because, well, I actually can do it now because somebody gave me a tide-binding code which is written in Mathematica and is very nice, but otherwise I wouldn't have been able to write my own code to diagonalize this type of problems. But this I can do it myself starting from scratch. I just open a Mathematica notebook and I write the formula and I get it. Which is quite nice because, you know, I don't have to do any numerics, any diagonalization of a lattice. I can just write with the green. I can start with the Green's function, which is very simple. I can put the impurity, write the formulas for the T-matrix, and I get this. So I'm very happy that that it works. So, and I recovered the physics, which I would otherwise get in a much more complicated fashion. Okay, good. So this I'm not going to talk about it maybe. Okay, in the last maybe half 1 hour or less, I have two more techniques to tell you about. I mean, I'm going to switch gears again, so if you have questions about this technique, I mean, let me know.
So, the impurity is the magnetic potential?
No, it's just a chemical potential on site.
But it's different for...
No, this is a spinless. This is a spinless, so this is electrons and this is holes. That's why it's 1 and -1. Because one is C dagger C and the other one is minus C dagger. It's electron hole, that's why it has an opposite sign. It's not magnetic. You can do a magnetic one also, but I don't know what it means physically. I usually do just a non-magnetic one. Yes.
Yeah. So I have a question. Just if you go on the next one. So just to just to summarize, basically you are saying that this plot is obtained by looking at comparing the T-matrix. You still have to diagonalize.
No.
You still need the spectrum of the non-interacting function, but the infinite system.
Exactly.
You don't need to do any finite size.
No finite size. I have a G0 of K,
Yes.
which is a 2x2 matrix or a 4x4 matrix. I plug that into a formula with G0 times T times G0, and then the only thing I need to do is an integral in K. This type of integral in K over the Brion zone. That's the only thing I sometimes need to do numerically is an integral over the Brion zone. Yes.
And what is shown here is the density state.
Yes, it's some sort. It is a spectral function, which is simple, but it's averaged over the position perpendicular to the so that it corresponds more or less to some physical quantity. I can also do it exactly on the edge if I want, or I can do it. But here I decided to do the average over the position perpendicular to the edge.
Yeah, and somehow the physics of the fact that you have this impurity and you come to the thing and you see exactly the bound state is because it's the last scattering.
Because when I have an electron and I have an infinite boundary, an infinite potential, so it's the same as basically having a cut in my system. Yeah, because everything that comes in goes back. So yeah.
Without the equilibrium amplitude,
The bulk to get the states on the boundary has to be topological. So if I didn't have a topological bulk, then I wouldn't have any states on the boundary.
So I'm taking the limit for E to 0. I mean, you would expect to have no edge states?
No, when U goes to 0, I have no edge states, I have no edge. So U is if I take U to 0, I only have a bulk.
Okay.
U equals 0 is just an infinite system, uniform. When I didn't do it, yes.
What is the meaning of the sign of this spectral function? I mean, so for T spectral function,
Yeah.
yeah.
It's a correction to the because I don't put the spectral function of the bulk here. This is just a correction due to the impurity. So you can think about the sign as in some regions I have more states than in the bulk. In some regions I have less states than in the bulk. So it's a correction to the bulk spectral function, which would basically cover this whole part. This whole part would be bulk, and this is just this correction is changing the bulk spectral function. That's why it's positive and negative.
So it's like weight transfer from bulk to weight.
Yeah, exactly. Mm-hmm. Yes.
You have the idea of the energy scale of this heat to get this velocity?
I would assume it has to be much larger than T. T is the bandwidth.
Okay.
I usually take it about 100 times the bandwidth or something like that. But I can see the transition occurring probably around a few times T, something like that. Here it's 1, so it's equal to T. You see that I'm still well separate from, well far from that. And here it's 100 times the T, which is the hopping term. So it's, I need it to be much larger than T, which is the bandwidth.
The second question, for the definition in the T matrix, can we have some singularity when V has some values, so the denominator of this T matrix will vanish?
Yeah, exactly. So that's exactly what gives me these poles here.
Okay.
So when this is going to, that's how we calculate the poles. We take this to be 0, and then it means I have a pole in the T matrix, and this gives me the peaks, which are the bound states. But I'm adding some I delta to the omega, and this gives me not infinite things, but some sort of rounded off stuff, because I'm adding an imaginary part to the Green's function. So then these peaks don't just go to infinity, but I have some sort of finite width because of the imaginary part which I'm adding to the Green's function. Okay, good. So I'm wondering. I had a few words to say about the bulk topological invariant. I don't know if I should talk about that a little bit, and then I wanted to talk about another technique which we are using to describe Majorana, which is the Majorana polarization. So this one I'm not going to talk about it, but yeah, I don't know. I'm kind of hesitating which one to do. Okay, let me tell you about this. Probably is more. The other one, it's not even very rigorous because people do it, but they don't justify it very well. So I can tell you more if you're interested. So another thing which we used a lot when we talked about Majorana, which is some nice quantity which we introduced. We called it the Majorana polarization. If you heard me talk about before, maybe you heard about it. So I talked a lot about the local density of states. So the local density of state is telling you how many electrons I have at a given position, at a given energy. So Majorana polarization, which we introduced, is more or less the same thing, but for Majoranas. It's telling me how many Majoranas I have at a given position at a given energy. Okay? So it's a quantity, mathematical quantity, which is telling me how many Majorana states I have in a certain region and a certain energy. So it's quite nice because when I have a model and I diagonalize or I solve it using these techniques, I get some states, but I don't know how many of them I have and if they are Majorana. So this technique is allowing me to characterize the solution of my Hamiltonian in terms of Majorana. And ideally, if I would have a measure of this quantity experimentally, then I would solve the problem of solving Majorana, of measuring Majoranas, because then I would do the experiment and I would say, oh, I have this many Majoranas here. Because this is a mathematical quantity, but experimentally we still haven't found a way to make the connection to possible measurement. And it's my fault also because I haven't spent too much time on it. So I spent time on other things, but I think there may be a correspondence to some experimental measurement of this quantity. Okay, so just let me start with something more basic than that. So I told you that Majoranas were combinations, equal combinations of electrons and holes. So I need some quantity which characterizes the superposition between electrons and holes. Some quantity which quantifies this superposition of electrons and holes in components in a wave function. So if I have a general wave function, here I draw it quite graphically. It was from like the talk which was given for a very general audience. So a given wave function is a superposition of electrons and holes. In the language that I told you I used till now, I would have this type of combination. Okay, so I had a coefficient coming with an electron, and I have a coefficient coming with the whole component. And you remember from the tight binding, the computer speed solutions which have, and I know the coefficients of the electron and the whole component of my solution. But how do I know if these solutions are Majorana or not? I can look by eye and say, oh look, the electron component looks exactly like the whole component, but sometimes it's not so easy, because sometimes I have, for example, spatial distributions. And there it's a bit tricky, because spatial, if I have a state which is distributed in some region, then I don't know exactly what's happening. I'm going to show an example immediately. So what we introduced was this quantity, which is a product, more or less, between the electron and the whole coefficients. And I see that this quantity is maximal if these two values are the same in absolute value. And it's 0 if I have only electron or holes. So intuitively satisfies the condition. It's 0 for electronic or Hall state, and is maximal for an equal superposition of electrons and holes. So more or less, it works. It was not so easy to get, because you could imagine also UV star, and that doesn't work. So it's very hard to justify why it doesn't work, but we did a lot of examples, and this one was not working. So you have to have this exact combination of the coefficients. Okay, so for a spinless model, it's that. And then if you remember, I told you in the first lecture, then in general, I don't have to have an equal combination of electrons and holes. I'm free to have a phase, a relative phase between the electron and the whole component. And you see that for a state like that, which has a relative phase between the electrons and the hole, the polarization acquires a phase also. So this polarization is capturing, is a vector, and is capturing the phase, the relative phase between the electron and the hole, and also the overall phase of my wave function. So this polarization is a vector in the complex space, which basically incorporates information about the relative phase between the electrons and the hole, and of course of the magnitude of the electron and the hole component. And you're going to ask me why an Andreev bound state, which is a superposition of electron and the hole, is also not a Majorana at zero energy. And then the answer to that question is that I need to also look carefully at the spin. Here this is a spinless model, but in reality I also have spin. So if I were to have an equal superposition of an electron with a spin up and the hole with a spin down, then I didn't have a Majorana. Because if I take the Hermitian conjugate of that, then I get something different. I get a C down dagger plus C up, and I'm starting with a C up dagger plus C down. So an Andreev bound state for a regular S-wave superconductor, which is a combination of C up dagger and C down, is not a Majorana because of the spin. But the spin, this is very tricky. If I didn't have the spin, then the Andreev bound state of the S-wave superconductor could be Majorana. But they are not because of the spin. In order to have an actual Majorana, I need to have a superposition of the electron with the spin up and the hole with the spin up. Because only then I can take the complex conjugate and I get the same thing. So then the Majorana polarization needs to have some spin structure. So it needs to capture this information that I need to look only at the coefficient. I need to look at the electron hole superposition of the same spin, not with opposite spin. So that's why the Majorana polarization for spinful models is a product of U up V up and U down V down. You know, it's only looking at the superposition between an electron and a hole the same spin. It doesn't look at the superpositions of electron and hole with opposite spin. So, and this is crucial because this makes a difference between something which is really telling you something Majorana state and something else. So the spin is really a crucial ingredient. And again, like what I was saying in words before, this is a vector, and its magnitude is giving me the superposition of electron and hole, and it has a magnitude of 1 when I have a full superposition, so Majorana, and the phase is telling me is basically related to the relative phase between the electron and the hole component of a Majorana state. And it's oftentimes related to the superconducting phase of my system, but not only. Okay. So for a single state, for a single position, for a single site, or for something that doesn't depend on position, it's very simple. Okay, that's how it is. But complications arise when I have a spatial distribution, and that's where this quantity is actually very useful, Because if I didn't have a spatial distribution of things, then well, it wouldn't be so it wouldn't be so important. But in physical systems, I have some spatial dependence always. So I need my Majorana polarization to be a spatial dependent vector. And what I do, I define it on each side using the components of the wave function, which, like I was telling you before, for example, in the tight binding diagonalization, they are spit out by the computer when I calculate the eigenstates and the eigenvalues of a Hamiltonian. So on each side, I have this type of vector, which again relates to these products between the electron and the Hall coefficients of the same spin. So this Majorana polarization is a spatially varying vector. And the criterion to have a Majorana state, and this is important, is that the sum of all the Majorana vectors in a given region is going to be equal to the sum of the density of states in a given region. So it's not enough to have locally that the Majorana state, that the Majorana polarization is 1, so it's maximal, and it's not even 1 in a spatial distribution. It's equal. The maximal value is not 1, but it's the local density of states, because the local density of states integrate over given region is 1 maximally. So on a given site, the maximum Majorana polarization is equal to the local density of states. I can have just a part of the state there. I don't have the whole state concentrated on one site. I have a part of it, and the maximal polarization, which is UV, the maximal value of UV, 2UV is U squared plus G squared, which is the local density of states. But I also need to have all the Majorana polarization vectors to be aligned. So it's not enough to have just locally like big values of the Majorana polarization. Also have some sort of ferromagnetic state in the Majorana polarization. So all the vectors have to be aligned, because sometimes non-Majorana states have locally Majorana character, but globally they don't, because the Majorana vectors are being, disordered. The position, the direction of the Majorana vectors is changing with respect to position. So, and I'm going to show you an example when this happens, and it's quite interesting, because if you don't have this criterion, you cannot guess if a state is a Majorana. You don't have another criteria to say, because the energy can be quite low, so it's close to 0. I have locally some Majorana character. How do I know that the state is a Majorana or not? So, well, maybe I'm not going to show the most basic application, so I can apply it to a chains, I can apply it to ribbons, and the most interesting part is when I apply it to strips. So when I apply it to chains, I'm going to see something on the ends, but here, in a strip, I have two directions. I have a finite size in one direction, and I have a finite size in the other direction, and you can imagine that if I were to have a square, the Majoranas would disappear, because Majoranas are some states which are living on the ends of the chain. But if my system is becoming a square, the two Majoranas will go where? They don't know where to go. So then it means that the state is kind of ill-defined. So there is no longer really a Majorana. So when I'm going from this type of system to this type of system. So.
But how do you know the orientation of polarization on one chain? It can be this way or opposite. They can be aligned, but in the opposite direction.
Yes. Oh, I'll show you just a second.
I have fermion.
Okay, let's see. Well, I don't. Yes, they could be. I don't need to see if I have a. Okay, well, I'll show it. Here is the one example. So I'm plotting the Majorana. The Majorana polarization is a vector.
Yeah.
When I calculate it, on one end of the wire is in one direction, on the opposite end of the wire is in the opposite direction, and I have to. It has to be like that because the integral of the polarization over one system has to be 0. Because I cannot create Majoranas in one system. The total sum of my Majorana strings has to be 0 because I cannot have three Majoranas in one system. So when I'm integrating, I have to integrate over the region where I know that the Majorana has to live. I cannot integrate over the whole thing. When I integrate the whole thing, it's going to 0, of course. So in this case, the polarization is pointing up here and it's pointing down here. So I have two oppositely polarized Majoranas on the threads. So that's the.
So in a given sample, it will not be completely ferromagnetic like you.
Yeah, it's ferromagnetic on one side and ferromagnetic on the other side with yes, with opposite in opposite direction. Yes. So for this chain, we computed it, and we looked at the criterion. We saw that indeed this criterion is satisfied in the topological region. It's the ratio between the Majorana polarization and the density of state is equal to 1, exactly in the topological region, which was predicted by the, whatever other criterion we have for this type of system. So it was working for the 1D chain. But then when you start to look at more complicated problems, for example, like here, so here I do the same thing. I'm looking at the integral of the polarization along this region. I divide by the dose. And again, I didn't draw the vectors, but the polarization here is pointing in one direction, and here the polarization is pointing in the opposite direction. I think I have it, but I'll show it in a second. You see that this is the phase diagram. These are the topological regions, and it's exactly the same as what is predicted by other type of calculations. So this Majorana polarization is working. For example, for a three-chain problem, and you see the topological phase is becoming quite messy. The moment I'm starting to have a finite width, the topological phase diagram is becoming messy because the perpendicular direction is adding some complexity to the problem. And if my system is very wide, the topological phase diagram is becoming really bad. And what's actually cute is that you have these regions which here they are yellow. I mean, you can think about what does yellow mean, because I have the red, which means I have Majorana. That is blue, I mean I don't have Majorana, but I have this yellow. And what does the yellow mean? And I draw the figures. So look at this case, like what Natasha was asking. Let me see. Oh, here. This is okay. So look at one particular situation. Here you see the vectors. Maybe you don't see very well. They're all aligned in this direction, on this side, and on this side they are all aligned in the other direction, oppositely. If I sum over this value, over this region, the Majorana polarization, then I get it to be equal to the local density of states, and these are the red regions. You see, I have ferromagnetic behavior and ferromagnetic behavior on the two opposite, in the two opposite regions. But I have some other distributions of the vectors. Here I have a vector like that and a vector like that. They're also large. They're almost the same magnitude as these ones. But they're oriented oppositely. And if I look at the sum over this, it's going to be actually 0. And I'm in this blue thing. I have a fully non-topological case. Even if locally I have Majorana character, globally I don't have it, because it's just coming to 0.
But if you integrate it on another graph,
no, it doesn't work. No, it doesn't work. If I were to integrate it like that, it still wouldn't go. It still wouldn't be maximal. I mean, I tried. It doesn't work in that direction either. And here it's normally that my system has to make Majorana on the far away. And if here there is a lot of interaction between this one and this one, so I cannot separate it like that. And even if I separate like that, it doesn't go to 1. Okay, so here I don't have a Majorana that in these blue regions. In this other blue region, there's no Majorana character at all locally. The values of the arrows is almost 0. You see 1 over 10 to the 5th. There is nothing, even a local character. It doesn't exist at all. And it's interesting because these lines are actually giving me the bulk topological phase. That's why I have even something locally, because the bulk for the 1D and 2D have some sort of topological properties. And this finite size system remembers that in the bulk there is something, and that's why it forms this kind of funny distribution. But the most interesting part is this one here. If you look here, I have locally big arrows, but if I go around, this is kind of changing direction. So it's like almost like a vortex. So it's like the Majorana vortex. So this state, it's neither Majorana nor Majorana, because when I calculate the integral and I divide it by 2, it's quite big. It's 0.7. So it's quite big, but it's not. But it's not 1. But it's not 0 either. So it's something bizarre. It's like a Majorana vortex, and we call it quasi-Majorana, and it only appears in the system in which the length is comparable to the width, or at least a few, 1/10, 1/5, whatever. And it has energy which is very close to 0. So numerically, you cannot even say if it's 0 or not, because you have to do a lot of, increasing the size a lot to see where if it's really going to 0 or not. It's very small energy. So these states, this type of states, are bizarre. And we don't know what they are. And experimentally, they should be there because this is, this type of system should exist experimentally because the length and the width are comparable oftentimes in an experiment. But from a theoretical point of view, we don't understand if these states are really Majorana or not, if they are abelian or non-abelian, what type of physics do they have. So we don't know much about them. But this technique of the Majorana polarization allows me to know that they exist, because otherwise I cannot predict them. If I look at the energy, they are zero energy, so I couldn't know they are different from the red and the blue from an energy criterion, and I wouldn't know from a local density of state criterion either, because they have some local density of states, which is more or less the same as for the other ones, so I wouldn't know if they have a special type of character if I didn't have the polarization. So this type of tool allows me to know that these states are different, in what way they are different. So that's more or less more or less the utility of this.
Uniquely, homogeneous correlation between full polarization and energy going to zero.
I think so, but it's very hard to say when you have a finite size system, because going to zero, then you have to do scaling, then you have to have numerics which are taking.
More narrowly, can I say that full polarization always means energy zero?
Energy zero for numerics, it's never actually zero. So
no, I understand, but you can do it somehow.
Full polarization means the energy is very, very small. That the most I can tell, the energy is very, very small. Quasi-polarization means the energy is also very, very small, but maybe not as small as for full polarization, though it's comparable. So that's what I'm saying. It's not, it's not a direct criterion, because for a finite size system, zero energy doesn't exist. So I cannot.
And there's some theorem manifold that you calculated that the energy must be zero to have a full Majorana. Yes, definitely. So no, and for an ideal system, you should correlate. So, and if I were to take the system to infinity, then this state. This should go to zero. This, I don't know if it goes to zero. Or this you should scale differently than these states. So, but these states definitely should go to zero, and I take the system to infinity. But these states, I don't know. So that's the thing. We don't understand. But this, you're right. I mean, in ideal system should go to zero. But when a system is finite, I always have some sort of finite energy, and I cannot say if it's zero or not unless I really take it to scaling. And the worst thing, the worst situation is to have this, which is a full square, in which I never have full Majorana at all. I only have this sort of quasi-Majorana in all my phase states, and I don't know really what they are and what's going to happen to them. So that was part of my project, is to dig more into this to see what type of statistics they have, if they are the same thing as Majorana, if they are different. Sorry? Actually, it's not Kane-Mele, it's a model with, it's like a Kitaev, it's like a spin-full Kitaev. It predicts Majorana, but it doesn't say anything about finite size squares. It says, yes, in an infinite ribbon, I should have Majorana. In a one chain, I should have Majorana. But the bulk doesn't say anything about the square, because the bulk is the bulk. I mean, the bulk predicts I have Majorana in here, but the bulk, a 2D bulk means that 1D boundary should have Majorana, but it doesn't say anything about 2D boundaries. So it's hard to say what happens when I add two boundaries and not one boundary in one of these things. So that's why this fully open systems with two boundaries, you don't know, because you cannot make boundary correspondence. So I think, I'll stop here. I mean, this is more or less what I wanted to say about this thing. So, okay, thank you.
Thank you very much.
More questions? Yes.
Yeah.
For your definition C, it seems like you cannot be seen as a topological invariant, because it can take some. No, it's not. I call it C, but it's not a topological invariant. It's like the criteria. For 1D system, can also take some fractional between 1 and 2?
I never found an example, but I assume. Well, let me see where it was. No, I don't have the figure here. I don't have an example of where a place where you can take fractional values. For me, it was only going from 1 to 0 in the 1D. Or the examples I took, it was either 1 or 0 or going in between the transition.
But I couldn't find any examples of fractional things, no.
Question? Yes.
Could you use the schematic method to study this quasi-topological phase you show at the end?
To use what method, sorry?
So for the quasi-topological
Yes.
state you have at the end for the square,
Yes.
Kitaev model, could you use schematic approach? Because then you have
That's a good question. No, because you have two boundaries. In the T-matrix, we could only get one boundary in one direction. In order to add a second boundary perpendicular to the first, then the T-matrix doesn't work anymore because you have already a bulk which is spatially non-invariant. So you cannot. That's one of our problems right now is how can we model corners? But we couldn't find a way to use T-matrix to model corners. So no. It was only numerics, other type of numerics, but no.
in the square model, if you just identify two of the sides separated by just join them together using a coupling that
Yes.
varies from 0 to 1. Would you just recover the ribbon?
I haven't tried, but I would expect to recover the ribbon. I haven't tried. Okay. I haven't tried, but I would expect to recover the ribbon, yes.
Okay, I think we can thank Cristina.
Thanks.